This is Learning Target 5.2. Notice our objective here is to define and apply rational exponents. Okay? What that essentially means, if it's compared to 5.1, as opposed to taking something raised to the a power, okay, where a was an integer, what we could see here is stuff like a over b, where our exponent is a rational number, which in math terms is really a fancy way of saying a fraction. Okay, so we're really looking at exponents that have a term in the exponent that's written as a fraction. Okay, that's learning those properties and to use those. That's what today is about. If you printed off the notes from Moodle, you'll see there's a huge chart just to help you out with squares, cubes, fourth and fifth powers. Get to know that chart really well. Be able to use it both ways. If you had 5 to the fourth power, that's a term that's on that chart. You'll see that that's 5 times 5 times 5 times 5. That's 625. Be able to use this chart both ways. That's, what it says on the chart is that 5 to the fourth power is 625. Okay? But from that, we should keep in mind that the fourth root of 625 is 5. Okay? Same thing here. The fifth root of 32, well, that's 2. But we should also know what that implies is that 2 to the fifth power equals 32. And in fact, for this example, this is what's on the chart. This isn't. But those two expressions really go together. They're saying the same thing, just in opposite ways. Same here. This is what you'd see on the chart. Understand it also implies that. So let's start to talk about a rational exponent. Okay? X to the a over b power. A is known as the power of the base. B is the root. Okay, so there's a couple different ways that we could write this if we wanted to simplify. We could just say take a, write it as an integer exponent, but then take the b root. Okay, notice I'm not saying square root because that would imply that b is 2, but take the square root of that whole quantity, x to the a power. Or we could take the b root of x and then raise it all to the a power. So essentially you've got this power of the base and the root represented by a and b, and whether you apply the power a or the root b first doesn't matter. You can do it in either order. What does become a little bit important is when we're simplifying expressions that have a rational exponent. Technically, both ways would be valid steps to make, but a lot of times, one way or the other makes it easier to simplify. Okay? I think you'll get a much better understanding of what I mean by looking at examples. So here's our first little set of problems that we could see in Learning Target 5.2. 4 to the 1/2 power. Okay, just to apply what we just saw, this says that if we take 4 to the first power, because that 1 represents the power, the 2 is the root. So I'm taking the square root of 4 to the first power, which is really just the square root of 4. It ends up being 2. This is one you should get familiar with because you'll see it a lot. Raising a quantity to the 1/2 power is the same as taking the square root. Now we could throw in some negatives again. That's no big deal. If that's the case, if we put that exponent down in the bottom, it becomes positive, just like if the exponent was a whole number. From here, we would just simplify it really a lot like the one we just did, where I take 1 over the square root of 4. That would end up being 1 over 2. Now, if you looked at that one and thought of a different way to simplify that, that may be totally legit, but it should lead you to 1/2. 125 to the 2/3 power. So the power is 2. The root is 1/3. All right, so what I'm going to do here, and this is where it just takes practice. I can tell from looking at this, because 125 is a big number. There's two different operations I could do. Take the third root or square it. 125 squared is going to be a really big number, bigger than I want to work with. So I'm going to take the third root first, and this is kind of the first case where your chart would come up. Okay? 5 to the third power is 125. So what's in the parentheses would simplify to 5. Okay, that's the cube root of 125. Then I would square, and 5 squared is more manageable. Again, just like in learning target 1, if we have a fraction like this, we could certainly go ahead and apply the exponent to both components of the fraction. Now notice here, I left something out. I just applied 1/2 because this is another property that came up. Multiplying through the parentheses. Okay, I'm going to leave the -1 on the outside. All right, now I can do that because -1 times 1/2, well, that would be -1/2, and the same down there with the denominator with 25 to the 1/2. So I've still got this 1/2 sitting out there, 49 to the 1/2 power. Hopefully you've seen by now. Okay, that's the square root. Same on the bottom. Square root of 25 is 5. And then, to make this to the first power, I would just take that fraction and flip it. 8 to the 1/6 power to the -2nd. Another case where I'm going to apply one of those properties from learning target 1 and multiply through those parentheses. When I do that, I'm going to get 8 to the 2/6 power, or 8 to the 1/3. That means the root is 3, the power is 1. That's just it's kind of like this one right here, where this was taking the square root. If you see to the 1/3 power, that's taking the cube root. Okay, so that'll be 2. Try a couple with some variables. Okay. My goal here is to write these as, because I can't simplify these to answers like I did before. But I can rewrite them with exponents that have fractions. Okay. This is taking the square root of x to the 3rd. Okay. The power of that exponent is 3. The root is 2. So that would be the same as taking x to the 3/2 power. Okay. Here I have 8 to the 1st. And in fact, sometimes, I'm going to split this up with the real number. And I'm not going to write that as an exponent with a rational exponent, because that's going to simplify to a whole number. But the first thing I'm going to do is just get those two terms split up. Cube root 8, cube root r. Because here, cube root of 8 is just 2. R, I'd have to rewrite to the 1/3. Its power is 1, its root is 3. So that would be 2r to the 1/3. Same thing here. My first step is going to be take these three terms and split them all up. By taking the 4th root. Okay, another example here. And this is another one where you'd have to think about the chart. Is there a number on that chart, okay, that I would raise to the 4th power to get 81? And you'd get, there is 3. And what you'd look for on the chart is, I've got the 4, I've got the 81. Is there anywhere on that chart that has some number that to the 4th power is 81? And there is. Okay. 3 to the 4th is 81. This could now be written as m. I'm going to simplify two things in one step. Instead of making it negative 2 over 4, I'm just going to make it negative 1 over 2. This will be n to the 3 over 2, because it would be written as the 6 over 4. Now, in terms of a final answer, I'm okay with these fractions. I don't like the negative, so I am going to throw that down in the denominator and make it positive. Okay, and that would be as far as I could go to get a simplified answer for that problem. We can do some solving. Okay, using these properties to solve. Really basic one right here. When we're solving an exponent, what you need to get is that base the same. If you do that, you can pretty much ignore the base, and then you can just set the exponents equal to each other and solve. Okay, that's a pretty straightforward one because the bases are already the same. Look at the second one where it's not. What I would do here is look to see, could I take 9 and somehow rewrite that as an exponent that has base 3? The square root of 9 is 3, so I could say 3 squared is 9. Now that x is still on the outside of the parentheses, which I can just multiply through and do 3 to the 2x equals 3 to the 5th. There I get my common base. And what I can then solve is just 2x equals 5. To make that equation true, x would have to be 5 over 2. Well, let's look at one here where the difference here is I'm solving for the base, is what's going on. I want to show you how to do these. I'll do one, and then I'll leave 2 of them for you to practice on your own. Okay. I'll take a look at this first one. Very first thing to do here is divide by 4. I get x to the 3 over 2 power equals 8. Okay, now here's where I have to keep in mind what the meaning of this rational exponent is. Okay, it's saying that I could take the cube root of x squared, and that will be equal to 8. Again, whoops. Actually, that's not what it's saying. I was just kidding. It's not what it's saying at all. What it is saying, hopefully you caught my mistake here, is that the square root of x to the 3rd, I took my power and my root and switched them. Okay, the square root of x to the 3rd power equals 8. Well, when I rewrite it like this, much easier to solve. What I can do now is say, okay, square both sides to get rid of the square root, and I have x to the 3rd equals 64. Then I can take the cube root to get the cube to cancel. This would kind of come back to my chart. Okay, the cube root of 64 is 4. Okay? So once you get that exponent isolated, use the properties that we've talked about to rewrite it like this, because that sets you up with some operations that you can more easily solve. Okay? Square to get rid of the square root, cube root to get rid of the cube. Okay, these two right here, because I kind of got out of control here with my work. I'll leave those. Give those a shot if you want to look at those more in class, if you're still confused on solving when the exponent's in the base. Let's talk about one of those two. Alright, just a few applications as to where this kind of thing can come up. Here we're looking at the price of moon boots, which are going up. You can see we got a positive growth rate here. Not exactly sure what moon boots are, but I hope you see the idea here that we're kind of using a silly example because we're trying to drive home the point that what is the object? Well, it doesn't matter what it is. It could be a car, it could be a hamburger, could be moon boots, house, doesn't matter. Okay, same properties of exponents apply. But I can tell from this equation that moon boots are 62 bucks. Okay? And here's a question where we need a rational exponent. What is the cost in 2.5 years? Yesterday, with integer exponents, I could not answer this question. Now I can. 2.5 is 5/2. So I'd have 62 times 1.05, and then there's my rational exponent. I'd raise that to the 5/2 power to get the cost after 2.5 years. I'm not limited to the nearest whole year, which we were before. We'd be limited to just talk about exponents that were whole numbers. What were they 6 months ago? 9 months ago. I should say one final thought with this. From there, you'd have to punch that into a calculator to get a decimal approximation for what the price of moon boots are going to be in 2.5 years, given their price is going up 5% per year. 9 months as a fraction is 3/4, but this is talking about 9 months ago. So for t, I'm going to plug in -3/4. Another example, I'll leave you to simplify that on your own. Make sure you evaluate the exponent in your calculator first. And here, be careful when you're dealing with an exponent that's a fraction, put it in parentheses. Okay? Put that in parentheses. But I'll leave those two for you to finish it off and evaluate and get those final answers. That's all for 5.2. That's exponents that have fractions, and let's talk more about any questions you have in class.